handful of degrees and licenses in mechanical engineering, Chris Callahan works as the Extension Agricultural Engineer at the University of Vermont. Through multidisciplinary projects that deliver practical, cost-effective, safe, and sustainable results, Chris's work supports the analysis, design, evaluation, and adoption of infrastructure and equipment that meets the needs of relatively small-scale producers and processors in Vermont's food systems. Doug Schaffler works with the Power and Machinery Thrust in Penn State's Department of Agricultural and Biological Engineering. With a background in machine design and fluid power, his interest has been in agricultural and construction machinery. Farm operations at Penn State has used biodiesel and straight vegetable oil as alternate fuel sources and has explored the production of vegetable oil for use in the university dining hall deep fat fryers. These experiences have afforded Doug working knowledge of oil production, processing, and markets. In today's webinar, Chris and Doug will explore on-farm use of oilseed crops like sunflower, soybeans, and canola for fuel replacement and feed production. They will discuss small-scale oil extraction in terms of machinery and processes, as well as applications for resulting straight vegetable oil, further processed biodiesel, and seed meal byproducts. So at this point, Chris and Doug, you can take it away.
Hey, thanks, Sarah. How's the volume? Can you just give me a quick check?
Sounds great.
Okay. This is Chris Callahan. I'll kick it off. Thanks for joining us. And Doug will be joining. We'll be taking over about the second bit here. Give me 1 second. This is the rough outline we're planning to cover today. I want to talk a little bit about production and processing, and that's how I sum that up is from seed to oil. And then Doug's going to talk a bit on using straight vegetable oil as a fuel based on his experiences at Penn State. I'm going to speak a little bit about the option of converting oil to biodiesel and when that makes sense and what some of the benefits of that are, and also talk a little bit about some of the farmers I've worked with who are doing it on farm. And then finally we'll wrap up with Doug speaking about culinary oil considerations and producing oil for the food market. As we go along, if you have any questions or if something is not quite clear, feel free to type the question into the chat box on the lower left there. I also just want to say my work in this area has been supported by the Vermont Sustainable Jobs Fund and the Vermont Bioenergy Initiative. These are two programs underway in Vermont that have supported on farm scale biodiesel production for quite some time. I've just pasted in links to those two organizations in the chat box. This is a rough overview of essentially everything we're going to be talking about today. I think we got just about everything here, and we start with trying to get the arrow here. There we go. Starting with oilseed crops on the left-hand side, those are generally crops that require combining in order to make them into a useful form for what we're talking about. There's a cleaning, a drying, and a storage component to this, and then we're going to spend quite a bit of time today talking about this next step, which is oil pressing. Once you've pressed the seed, you end up with two products, meal and oil, and then those two things can be used for a variety of purposes.
Chris, this is Doug. When you started up the arrow, it seems like we dropped a lot of your audio.
Sarah, it looks like some folks are having audio drop in and out. I don't know if there's anything we can do about that. Yep. Yes. I'll not use it then. Okay. And the pictures there are soybeans, and then there's flour in the left center, and canola on the right center, and then finally black bottom, just to give people a visual of what we're talking about. Resource that's available for folks, and it's the oilseed production in the Northeast manual. Heather Darby, a colleague of mine here at UVM, and her team just wrapped that up. And I've just pasted in a link to the PDF where you can download that. It covers basically the research done on oilseeds in the Northeast over the past 7 years, and it's quite complete. So I urge people to take a peek at that. Funded by Northeast SARE. The other thing I want to point out, which I'm not going to get into a whole lot of detail on today, but is another resource people might find useful, is the Oilseed Cost and Profit Calculator. Again, I'm putting in a link to that in the chat box so you can get directly to it. This was, it's an Excel-based calculator, but you don't need to know a lot about Excel to use it. It walks you through the basic cost calculation of oilseeds. On the left-hand side, there are all the, in steps 3 and 4, labeled 3 and 4, are basically the crop production costs getting to seed. And then there's a section underneath that for the cleaning and drying component. And then in the center section, starting with step 6, we account for the cost of pressing the seed, followed by the cost of biodiesel production if you choose to do that. And then finally, a place to put in market value of the product so you can determine potential profit or loss based on your assumptions. And one of the nice things about this is it lets you look at a bunch of different scenarios, both in terms of yield, but also in terms of potential investment in an operation. And it also provides what we call typical values. So if you're stuck on something, you don't quite know what that factor might be, you can use the assumption there, at least as a starting point. So let's talk about getting from seed to oil a little bit. This is a fairly typical farm scale oilseed press, and this one is a Kerncraft model KK40. This one happens to be at Borderview Research Farm in Alburgh, Vermont. And the terminology that people use with oil presses does vary quite a bit, but this is what is fairly common. There's a hopper up top which receives the bulk seed. There's a motor in the back left on the left-hand side of the image, and that's what drives the press generally. They are generally electric motors with VSD, variable speed drives, so you can adjust the speed of the press. Some, they may or may not have a gearbox. Some are direct drive from the motor to the press. The part coming off the front of the press, in this case there's 2 of them, we call a barrel. They will often have a heater attached to get the barrel and the seed up to temperature for proper pressing. Finally, you have a nozzle or a die, and that's the restriction in this process, and that's what creates the pressure that allows the seed to be crushed and the oil to be separated from the meal. You can see that a little bit better in this next image. This is that same press with the one side essentially taken apart, and then the upper left-hand corner that you see an inset photo there, I've taken off the collar, and you see the star shape, the 4-point star. That mates up with the end of the screw or the worm. And what happens here is from the hopper, will go down into that screw, which is turning, forcing the seed forward away from the press. When it hits that star die, it undergoes pressure, which crushes the seed. The pressure also forces oil back and the meal through the nozzle, and then the oil drops off of those perforated sieves that are also around the barrel. That's the basic pressing process. This is what it sort of looks like schematically. We start with seed on the left-hand side, And the idea behind this image is to show how the costs get allocated between from seed going to the two different products of meal and oil. On the left-hand side, we have sunflower seed, which in this case is assumed to have cost $338 per ton to produce clean, dry seed that has about 38% oil in it and 62% solids. When you press that 1 ton of sunflower seed, the cost is fairly minimal. You'll notice compared to the cost of production, the pressing cost is only about $2.40 a ton in this case. And so the cost of pressed seed is just $340 per ton. Incidentally, what we found is cost of production on a per ton basis in some of our farms is quite low compared to national averages. We have the differences have to do with scale and also fertility of soils. So that was a somewhat surprising result. We found we actually need less nutrients in some cases to produce these crops than the areas where they're predominantly grown. So after the press, you have oil and meal, and the first step of this is showing that 1 ton of seed being split out into its fractions of 0.38 tons of oil and 0.62 tons of meal, and the cost is just split accordingly according to that fraction, and then you can end up with converted costs on a unit basis per gallon of oil of about $1.28 and per ton of meal of about $340. One of the in our work, a number of different presses available on the market, more now were just a few years ago. And one of the things that we've struggled with is, which press to buy, and once you buy it, set it up and use it most effectively. They are quite adjustable. You can adjust the speed, the screw. You can adjust the nozzle size. There are even some screw types. And so we a protocol, and so we used a common protocol in looking at them. And we, in addition to measuring performance, we also tried to capture operator and owner feedback on the presses. The full report can be downloaded as a PDF, and I'm going to paste that into the chat box here. And there's also a video that accompanies it, which some people may find helpful. The video includes interviews with the press owners, so you can hear in their own words how things run. And so some of our general findings from this press evaluation is the operation of a press currently depends on a lot of trial and error, and a lot of operator tips and tricks have been captured as a result of this and included in that report. The other things we found is the press capacity often differs quite a bit from what the published specifications are, and it depends also on the oilseed being pressed. The other neat thing we found was maximum oil yield. In other words, getting the maximum percentage of oil out of a given batch of seed is generally below the maximum press capacity. And so there's a peak, and I'll show this in the next slide, there's a peak of net oil yield that's in the mid-range of the pressing rate or the motor speed. And then lastly, phosphorus, the amount of phosphorus in the oil declines with pressing rate as well. And Doug will speak a little bit, I think, to the importance of phosphorus later on. This is a graph showing 3 different presses. You can see the Ag Oil M70 is on the left-hand side, then the Kerncraft KK40, and the Tabby 70. And we did 3 different oilseed crops for each press. And the thing I want, the results that are circled here are showing how on the left-hand axis is net oil yield. That is the amount of oil taken off of a fixed amount of seed being pressed proportionally. So you can see that there's a peak in that figure of net oil that's not at the maximum pressing rate, the amount of pounds pressed in 24-hour period for each press. That's important in our case because many of our presses are under capacity. They're not being used fully. So if one is seeking to get the maximum amount of oil, you can press more slowly and do that. And so in this case, you can see a 15% increase with by pressing at half the speed in the case of the KK40 doing sunflowers. And then this is just showing peak oil yields for those cases. Some other processing that may be required and which are dependent on the end use. Most of our growers are doing settling, initial settling of bulk sediment. There's some solids that come through the oilseed press and into the outflow stream of oil, and so those need to be settled out. And that can be done in a pretty simple setup of a submerged outlet, tandem submerged outlet tanks, sort of like a septic tank setup. Filtration is also commonly employed, and I think Doug will speak to some specifications on that when he gets into used vegetable oil or straight vegetable oil, and then a process of RBD, refined. Which we'll talk about in a moment. I think we're you the Doug, are you muted?
Doug Koffler.
There you go.
Going to pick up the next part on straight vegetable oil. One of the things, now that we've got the oil, Chris explained the procedure for pressing the oil from the seed and getting the oil, and then we'll talk a little bit more about filtration when we get back to the edible oil side of things. But one thing I wanted to speak to here is that oftentimes biofuels are spoken of as biodiesel or vegetable oil, and the two are used interchangeably. And on this slide, I just tried to show that on the left-hand side is what we're talking about for this type of vegetable oil. Is straight vegetable oil is just that. If you go to the store and buy some canola oil or sunflower oil or something of that sort, that is vegetable oil. On the right side of this slide, it shows that if you take the animal fats or vegetable oils and put them through the type of procedure that Chris is going to speak to, transesterification, you end up with biodiesel. And the two materials are different then. Straight vegetable oil is just unprocessed vegetable oil, and animal fats or vegetable oil transesterified to biodiesel is biodiesel. So they're two different things. And I'm going to be speaking about the straight vegetable oil side of things. So straight vegetable oil is pretty much the same thing that you would use to fry up a batch of French fries, only you're going to be using it as an engine fuel. Sometimes, if you've got just a few vehicles you might be wanting to use an alternative fuel in, this is an easy way to do it, but the engine may require some engine modifications. Generally, the oil is heated to reduce how thick it is a little bit because vegetable oil is much thicker than petroleum diesel fuel. So moving the oil into the diesel injection pump is more difficult unless it's heated, and in general, these engines are started on petroleum diesel fuel and then shut down on petroleum diesel fuel. So when the engine's warmed up, then it runs on straight vegetable oil. Some of the problems in the past, and probably will continue to be in the future because diesel engines are made to run on petroleum diesel, vegetable oils will sometimes lead to Additional particles forming inside the engine compartment, it said, on the pistons, inside the cylinder walls, on the valves, and also, as this picture shows, on the left-hand side and on the right-hand side, you can see the buildup on those diesel fuel injectors of particles that have built up and will sooner or later start to degrade the performance of the engine. And if they get thick enough on valves and whatnot, can lead and have led to engine failure. So there are times and types of vegetable oils that you don't want to use, and there are times that it might be perfectly applicable to be using vegetable oil. This is another picture of an engine that used soybean oil, and it led eventually to the failure of this engine. Soybean oil in general isn't recommended as a oil to be used as fuel because it does leave more deposits on the engine components than other types of vegetable oils do. This slide shows the difference in viscosity. If you look at over toward the right of the graph where it's showing 100 degrees C or about 212 degrees Fahrenheit, that's pretty close to where a standard diesel engine runs. And so the two are pretty close to the same viscosity at that point, but still aren't quite the same. And again, an engine is designed to run on petroleum diesel fuel, so the vegetable oil is going to be a little bit different when it's being burned in the cylinder, and it's not going to be usually quite as clean a burn, especially at low loads or low engine speeds. And then if you go toward the left of the graph, as the temperature is decreasing, and you get down there near 0 degrees centigrade or 32 degrees Fahrenheit, vegetable oil gets much thicker, and so it becomes more of an issue with different types of oils. As you get colder, just moving it from the tank up to the injection system. That's why most modified engines for vegetable oil somehow include a component where they heat the oil up to engine temperature to reduce the viscosity to get it to flow better. We have run diesel tractors on vegetable oils with canola oil as low as 20 degrees Fahrenheit, 10 degrees Fahrenheit without much problem. But below that, we started to mix petroleum diesel in with the vegetable oil at about 20% petroleum diesel and 80% vegetable oil to keep the oil flowing adequately for winter use. This slide is showing that per Elsbet, which is the name of a company that makes modifications for vegetable oil fired engines, that as far as they're concerned, canola or rapeseed oil is just fine the way it is. Press it, filter it, and use it. Sunflower oil, they would appreciate it if it's degummed to get some of the other solids out of the oil. And then for soybean oil, their claim is that you don't want to use it in an engine at all, that it does put more solids onto the surfaces of the engine than the other types of oil do. Here at Penn State, we had two tractors, or one front-end loader and one farm tractor, that were modified for straight vegetable oil. We used these for 3 or 4 years, and the front-end loader accumulated some hours, but the tractor accumulated more hours, up to about 2,000 hours on straight vegetable oil as fuel. And the way these engines worked in these two tractors, trying to avoid the problems of particulates or solids coming out of forming on the engine components at low temperatures or low speeds, was if you start at the left of this little flow chart, kind of ask the question, there are sensors on the engine, is the engine warmed up? And if the engine is not warmed up, if it's still warming up and still cold, then it uses petroleum diesel as the fuel. Once the engine warms up, then it moves on to the next diamond, and it asks the question, is the engine being loaded at all? Is it really being worked at all? And if the answer to that is no, then again it uses petroleum diesel fuel and doesn't switch over to the SVO fuel. Then when the engine is warmed up and it's pulling a load, so now it's plowing or disking or hauling a manure spreader or doing something that requires some power, then the sensor in the exhaust warms up and it switches then to the SVO fuel and uses the vegetable oil as fuel. So this takes kind of the guesswork and automates the process of somebody sitting there flipping switches and allows the fuel to switch back and forth between the two types based on the temperature of the engine and what kind of load is being put on the engine. This slide is just showing that in this particular setup for that tractor, the yellow line is showing the vegetable oil power for this tractor, and the red line is showing the diesel power. And it pretty much shows that there wasn't a lot of difference between the two. The electronics in the tractor, this particular tractor has an electronically controlled fuel system, and the electronics compensated for vegetable oil as fuel. And generally you would expect about a 10% drop in power if you're using vegetable oil as a fuel. The slide is showing at 1,370 hours, the New Holland tractor had used 3,400 gallons of straight vegetable oil and about 600 gallons of diesel fuel, petroleum diesel fuel. So it was using, by volume, about 85% vegetable oil. It was grown within 7 miles of the farm. And then the petroleum diesel that it was used to start with and then used when it was being used for low load applications was far less use, just 15% the other. Front end loader, on the other hand, shows about equal use between the two. And that really wasn't maybe as good an application for a straight vegetable oil machine. It was started and stopped a lot. It would load up a manure spreader, then sit, be shut off, and then it started up to do again. So it never really warmed up a lot of the time. And that was reflected in how much fuel it was going through as far as the straight vegetable oil was concerned. This graph just shows some of the use over time. Obviously, there's more use in some times of the year than others, and in the wintertime, there was more diesel fuel used than in the summertime. And that brings us back to biodiesel, and using diesel fuel or using vegetable oil and converting it into diesel fuel as fuel rather than using it as straight vegetable oil.
Thanks, Doug. This is Chris Callahan again, and I've made some adjustments to my audio, and I hope it's more consistent for folks. I apologize for that earlier on. If you're still having trouble, please make a note in the chat box, and I'll try to address it as effectively as I can. So I'm going to return to the chart that we started with. That is just the schematic or flow chart of the process. And what I'm going to focus on now, we talked about everything up to the oil press and through the oil press previously. I'm going to focus on everything downstream of that now, and that's the process of making biodiesel from vegetable oil. And there are a couple of reasons you may want to do that. Doug pointed out some of the limitations of straight vegetable oil, the need for engine modification, for example, cold weather performance and whatnot. And so times when converting to biodiesel may be beneficial to the farm or the operation. And so the basic processes making vegetable oil, no matter what the source,
Okay, we experienced some of the same audio problems with Chris again. So
I think I'm back.
Okay, Chris, if you wouldn't mind just quickly going over those introductory comments once more to redirect ourselves.
Sure, I'm sorry about that. So I'm going to focus on the lower right-hand portion of this chart now, which is everything after the oil press on the oil side of it. So regardless of the source of the vegetable oil, we're interested in whether it's been freshly pressed off of an oil press from a crop just grown, or whether it's been recycled from use in the culinary markets. First step is to filter it and settle it and get it as clean as possible. And in some cases, that might involve removing water from it as well. The next step is what we call the conversion process, and this is generally something called transesterification. and that's what really turns vegetable oil into biodiesel. There are additional ingredients involved here. We need to add some lye and some alcohol. The lye is a catalyst that helps the reaction take place, and the alcohol is essentially what makes the vegetable oil turn into biodiesel. And so after that conversion process is done, there's an alcohol recovery step where we always put in a little bit extra to make sure we get full conversion, and you want to get that extra bit back, and so that amounts to distillation. Finally, there's a settling step in which glycerin drops out of the fuel and can be taken off. And then there's a fuel cleaning or finishing that takes place, and I'll show you some examples of that. Finally, in order for something to be called biodiesel, it needs to pass a quality specification that's been established by the industry to ensure that it can be used in engines with little to no modification. I guess we just went over this. Sorry about that. This is the transesterification step, and this is a really simplified version of it, but I think it's helpful for illustrating essentially what's going on. We start with vegetable oil on the left-hand side. We add some lye, which is usually potassium or sodium hydroxide, and some alcohol, usually methanol, although ethanol can be used as well. And that's heated and mixed. We're trying to get a chemical reaction to take place, which will turn the vegetable oil into methyl esters or ethyl esters, and that's what makes biodiesel. And then there is a byproduct here of glycerin. And if we have time at the end of the presentation, I can talk about some of the work we're doing to make good use of that glycerin. It does turn into a liability for many small-scale producers of biodiesel. And I just show the alcohol being returned back to the process. I want to talk about two particular farms that I've worked with quite a bit. And who have been at this for quite some time. John Williamson is at State Line Farm in Shaftsbury, Vermont. It's a maple sugar and honey operation, formerly a dairy farm. John started producing oil seeds in 2005, and was really one of the early adopters in our area. He planted some sunflowers, canola, and you can see his new combine at the 1965 Massey Harris, just taken in that upper left pic. Over the years, John quite a bit of external through the Vermont Sustainable, the bulk of which oil barn, and this is stored for pressing oil seeds and for converting oil to biodiesel. And you can also see he's making use of some solar hot water collectors there to help heat his process for heating the biodiesel reaction. And then in the upper right-hand corner are a couple of test batches of biodiesel. And first time John started doing this, he likened it to looking at maple syrup sitting in the windowsill up at the sugar house. Inside the bio barn is John's biodiesel processor. This is a 400-gallon capacity main processor here in the near view. In the middle tank is where he mixes his alcohol and lye, and because those two ingredients are considered hazardous, he takes great care in when he's putting those together and handling them at all. The methanol, in fact, is loaded into that tank by drawing a vacuum on the tank and then connecting a hose to the methanol tank. So, and it's basically sucked into the tank from the transport container. So that's a clever solution to a potential hazard. There's no lifting of the methanol tank, which comes in 55-gallon drums, and everything is under vacuum, so spillage is actually quite unlikely in that case. And then finally, the cone bottom tank on the far end of that left picture is where the glycerin is settled out from the biodiesel. The yellow tanks you see on the right-hand side are a new addition to this setup, and these are the two big tanks are actually 1,000-gallon propane tanks turned on end, and those are used for finished fuel. The one that's on the right-hand side that's labeled biodiesel is the fuel that's just come off of the settling tank, and the two little towers in between the two big yellow towers are fuel cleaning equipment. There's two different processes that take place there. One absorbs water and soaps, and the other catches things like glycerin, free glycerin, and methanol. And so those are the typical contaminants that are left in biodiesel. And so what this is doing is really cleaning the fuel and making it become B100, which is what's stored in the far left tank. This is Borderview Farm, Roger Rainville in Alburgh, Vermont. Roger hosts the bulk of University of Vermont's research agronomy trials. There's quite a few done there. I think at last count it's close to 1,200 different plot trials every year, coordinated by Heather Darby. There is an annual field day up there that covers a lot of oilseed production and other agronomy topics. It's usually the first week in August. Keep a heads up for that. Roger has started out using a Chinese oil mill that was run off of tractor PTO. And he's since moved to the Kerncraft KK40 and an ag oil press that we described before. In terms of making fuel, Roger opted for kind of an off-the-shelf solution built out of, and he wanted, and this one, a biodiesel processor that literally gets delivered. Yep.
Chris, we lost you very quickly there. We
Sorry?
lost you right about when you just started talking about the technical specifications of his operation. So would you mind dialing back a bit to pick it up from there?
Sure. So this is a BioPro 190, and this is a 50-gallon biodiesel processor, and that's what's being used at Borderview Farm by Roger Rainville. He wanted an off-the-shelf solution. This processor basically gets delivered on a pallet. You plug it in, and you can start making fuel. It is automated, although you can also run it manually. And Jared, there on the left-hand side, is demonstrating good personal protective equipment. He's using gloves and goggles while working with methanol and lye and doing a titration. One of the most common questions that I get is how much does it cost to make a gallon of biodiesel? And the answer is it depends, of course. This is showing six different question here. How many acres are dedicated to oil seeds at Borderview Farm? It varies each year, as much as 30 acres in recent years, and that's a fairly common number around for the farms that I work with. Most of them are really just looking to make enough fuel to fuel their own operations at this point. Although I feel like that'll be changing shortly. Fuel prices are up again, and that's motivating a lot of interest. Cost of biodiesel. This is a summary of 6 different operations that vary very largely based on scale of operation, but also crop and cultural practices. And you can see the range of fuel prices there, from everything from about 97 cents per gallon to just I guess $3.75 per gallon. And you can see the difference in breakdown, what cost went into each, what the cost breakdown of each gallon is, and that's the helpful tool. That's the helpful part of using the cost profit calculator we talked about before. You can really break down where your costs are driven. And this is just showing an example of, if you're making 11,000 gallons versus 500 gallons, your capital costs get spread out over more gallons, and so your cost per gallon is significantly reduced. Back to you, Doug.
Okay, thanks, Chris. And last bit we wanted to talk about was once you've pressed the oil and you can use it for fuel, you can convert it into biodiesel. But kind of the epiphany for us at Penn State, we were standing in our oil pressing area once and we were thinking, we're pouring this oil into our tractor where we're basically offsetting, it was at the time about $3 a gallon diesel fuel, and at the same time the university's buying 20,000 gallons or so a year of canola oil to use in all the deep fat fryers on campus. We just kind of began to wonder what it took to actually do that process, and is that something we could ever do on a small scale to grow the seed, send it to the fryers on the dining halls, take it back from the fryers as used vegetable oil, make it into biodiesel, and then use it as fuel and equipment. And so with a bit of time and for this edible oil side of things, we, along with Chris and the folks at Vermont, we've been working with the Northeast SARE grant, just trying to figure out a little more about the processing of oils and edible oils and just what it all means. And we've had some help from folks in food science and other places to try to understand a little more about the oil and what the differences are. The slide is just showing small bottle. You might go to farmers markets and see oil sitting there for sale and kind of wonder what the differences are between that and what you buy in the store. And that's kind of an example of what the oil looks like when it's first pressed and has been cleaned. It's got a real golden color to it, and when you smell it, it's got a certain smell to it. Canola oil smells different than sunflower oil, and sunflower oil smells different than safflower oil. Each one has its own smell, and as a result also has its own taste. And olive oil has kind of built that into its own industry. That's what makes olive oil olive oil. You buy it for the flavor. And is there a possibility for some of these niche marketers and small-scale processors to take some of this oil and sell it at a much higher price than it's worth for fuel? So maybe they can make some fuel or use some for fuel, but then also sell some and diversify their operation somewhat. So just wanted to take a look at a couple things. First off, what's in canola oil? And when you look at vegetable oil and you talk about refining oil and what are you going to do to make it into the stuff you usually find on a grocery store shelf, well, if you take a look at a pie chart of any oil, it's got a whole bunch of different kinds of fats. You hear about monounsaturated and polyunsaturated and saturated fats. And then you've only got about 1% of this other stuff in the oil. And when you get into refining, that really is what they're trying to do, is get rid of this other stuff. And it's not much of what's in the oil, but it takes a heck of a lot to get it out of the oil. Some of those things that are in there that are this less than 1%, on the left-hand column we've got the antioxidants, things that you really want in the oil because they are keeping the oil from oxidizing, from going rancid. And those are the things like vitamin E, the tocopherols, and the carotenoids that also keep it fresh, keep it good. And then there are things in the right-hand column that are pro-oxidants, the things that kind of push the oil toward going rancid, toward oxidizing. And that's one of the things that supposedly this whole refining process is trying to do, is trying to keep it more stable, keep the oil more stable, give it better shelf life. So getting rid of the water, getting rid of the transition metals, getting rid of some of these other things, the chlorophyll that's in there, and gives fresh pressed canola oil almost sometimes a greenish sort of color. So how do you slow down rancidity? How do you prevent oil from going rancid? Well, there are different ways of doing it. Some of them are fairly easy to do on a small scale. Some of them are difficult to do on a small scale. And some of the work that we've been doing with food science is really looking like it doesn't even really help to do some of these things, that the raw oil actually is more stable than the stuff that has been refined and bleached and deodorized. And that goes against what all these folks in food science believe, and they've done it 2 or 3 times and are still trying to figure this out. But it really appears that the raw oil is more stable than the processed oil is. What are some of the things you can do if you want to keep oil more stable, even if it's raw oil? Some of them are pretty straightforward. The first one is to, for a while, never could say that word. Hydrogenated oils were the rage, making things into margarine, making them into hard fats, then they were more stable. And medically, that's not such a great thing to do. Second one there is to put something in it, use antioxidants to bind up these things that cause the rancidity or the oxidation to happen. One thing is to prevent exposure to light, so practically speaking that means use green or brown bottles. Don't put things in clear bottles. But unfortunately in clear bottles it looks a whole lot neater, so that's one of the ones you got to deal with. Avoiding high temperatures. The higher the temperature is, the faster things oxidized. So keeping oils at low temperatures in a refrigerator or even a freezer keeps it from oxidizing, and so will keep it good for quite a bit longer period of time. And the third one there is common sense. You just limit the exposure to oxygen. One way to do that is to put nitrogen or argon or some other inert gas over the top of these containers, either in the bottle or in a barrel or in a big vat, however you're storing the oil, is to keep a blanket of inert gas over it so that it doesn't have chance to touch the oxygen and so can't oxidize with it. The commercial oils you buy in the store are refined, bleached, and deodorized, RBD, and each one of these does certain things for the oil. For small-scale oil production, filtration is pretty straightforward. The right-hand photograph there is a filter press. They're common for filtering things like orange juice and beer and apple cider, apple juice, all kinds of things like that. And they oftentimes use diatomaceous earth, which is an inert ground-up material that pulls the particulates out of it. In the cylinder on the left, you see about 100 milliliters of raw oil that has settled, and you see about, out of 100 milliliters, probably anywhere from 5 to 10 milliliters of particulates that settle out. So anywhere from 3 to 10% is about what you pull out of the oil when you filter it. Some people think that if you leave that kind of stuff in there, when you're trying to sell a bottle of oil, that shows that it's natural, that that's in there. Other people think that it looks a lot better if it's a clear bottle of oil and you don't have to explain why there's all this other stuff in there. When it's filtered, usually it's filtered down to about you can get down to about a micron of filtration, which is really clean. You won't see anything else settle out of it in a bottle. The engines or the filters on a diesel engine are typically in the 12 to 14 micron range. Human hair is about 11 microns, so it gets the stuff out of it and can do a real good job of cleaning the oil. Second step, bleaching, is one we've messed around with because we really believed that if we could bleach the oil, we could really increase the shelf life. Since we started doing that and started really looking at the shelf life of the raw versus bleached oils, found out that maybe that's not true, that the raw oil seems to have a longer shelf life, be stable for a longer period of time on the shelf than the bleached oil is. That photograph in the upper right-hand corner shows on the right-hand side the golden yellow color of raw canola oil. Sunflower oil is much the same, perhaps a little bit lighter. And on the left-hand side, the bleached oil, something you're more likely to see color-wise in the supermarket. So bleaching oil, definitely, if you're using it in a deep fat fryer, does help to make the oil last longer. The material in that bottom right-hand corner, someone's asking a question, what's used to bleach it? The material in the bottom right-hand picture is 2 different types of so-called bleaching clay. It's a naturally occurring clay that on the left-hand side is finely ground. You can throw that into a vat of oil, heat it up, and then filter out the bleaching clay. And that clay kind of absorbs. It grabs onto the chlorophyll and other materials that are in that oil, and then when you filter it out, it takes them right out with it. The right-hand side is bleaching clay that's more in a granular form, and if you push the oil, hot oil, through that material, again, those particles adhere to the bleaching clay and stay behind, and what you get out is the clearer oil, the more transparent oil. The apparatus in the left-hand picture is just a way of bleaching oil that we put together. It's nothing fancy. It just heats the oil and then pushes it through. The long tube on the left-hand side is the bleaching material, on the right, the granular material. So we push it through some heaters, push it through that other material at about 25 pounds per square inch pressure. And that's enough to take those materials out. Then a deodorization is commonly done by bubbling steam through oil under a vacuum, and isn't anything that we've seen somebody doing on a small scale. We know a few people, one in Michigan, somebody here in Pennsylvania, who are trying to do some of that, but really haven't been doing that on a small scale as yet. So the refining primarily is filtering. Bleaching removes the colors, and they both can be done on a small scale, but it's really debatable whether the bleaching is necessary. Maybe if you're going to be selling to someone who's using it in deep fat fryers, that may be the reason to bleach it. That pretty well covers what we were, I think, going to go over. This last slide is the website for the University of Vermont Extension Crops or Oilseed Crop website, and that really is where a lot of information is for this. Anything that we've put together here at Penn State, we've been pushing up toward excuse me, Vermont, because they have already the website developed for that. And there are some fact sheets that we've put together on the pressing. There's the comparison of presses that Chris was talking about. There's a fact sheet on that. There's a fact sheet on filtering, one on storage, one on cleaning the seed, on processing regulations. What do you have to do to an area that you want to do this for? And that sort of thing. So they're also, every year in Vermont, for the last number of years, there's been an annual oilseed producers conference that lasts for 4 or 5 hours, and a lot of those presentations are also available on this website. They also have done yield results from various and sundry oilseed crops there. Those are there, and then there's some just articles on biodiesel production, oilseed pressing, and various and sundry things. It's just a good place to go for looking for information on oilseed pressing and whatnot, and even the production of the oilseeds themselves, the growing of them. So with that, I think we're pretty well done. Chris has put up a couple more informational pieces that are available, websites or the URLs for those. And with that, if there are any questions, we'd be more than happy to answer them.
Yeah.
Thanks for taking the time to listen with us. I hope you heard enough of it.
Thanks so much to both of you. For the participants, if you have a question, please type it into the chat pod, and you can direct it to one or both of our speakers today. I noticed that one of the resources that Chris has just shared relates to the break-even economics, which is one of the sections where the audio was cutting out a bit. So that link should give you a better look at what he was trying to say there. I have a question actually relating to that. So when you were starting to talk about some of the examples of programs or I guess individual endeavors that you've seen, Chris, you mentioned a Vermont Sustainable Jobs Fund grant. Could you give us some information as to grants and incentives for helping small-scale farmers acquire equipment necessary or capital in general?
Yeah, so it's dramatically different now than it was 7 or 8 years ago. At that time, Vermont growers were benefiting from a very, I'd say, a very aggressive program through the Vermont Sustainable Jobs Fund called the Vermont Bioenergy Initiative, with very strong support from Senator Pat Leahy. So there were really direct awards to several farms, four total, five total, that helped with some of that infrastructure development. So there's no real ongoing incentive to speak of. It was very much focused on getting some infrastructure in place, demonstrating the practice and technology. And we're at a point now where it's about leveraging the infrastructure that is in place to to produce more higher volume of fuel and drive the per gallon cost down. Does that help?
Okay, thanks. Yeah, as a follow-up question, we have a question from Eileen, who says she's looking at dedicating a small amount of acreage, so less than 10 acres of former farmland in Vermont to oilseeds, and she's exploring the cost benefits of this. You had mentioned before the value of economies of scale, I guess that you could say, where higher amounts of processing spread out the capital costs and overall lowered costs. So she asks if there's a minimum acreage for oilseed production that's recommended.
So 10 acres would be relatively small if you were going to be investing in all the infrastructure yourself. But if some of that infrastructure, for example, combining, pressing, oil conversion to biodiesel, if you can take advantage of some of the infrastructure that's in place already, that will make it much more feasible in the short term to get familiar with the crop production, for example, before you invest in some of that downstream equipment. You're fortunate, Eileen, being in Vermont, that we have quite a bit of infrastructure that you could take advantage of. There's pressing capacity throughout the state. There's biodiesel conversion capacity throughout the state. So 10 acres is not infeasible, considering making use of some of that infrastructure that's in place. If you were going to be, again, if you're going to be trying to replicate one of these models on your own, I think 10 acres would be on the small side.
Sure that we've understood your answer to Eileen's question correctly, and Pamela's question. There's not really a specific range that's offers a recommended scale. It depends strongly on what resources you can tap into in your community. And while 10 acres is a bit on the small side, it's certainly feasible under the right circumstances.
Thank you. Yep, that's clear.
This is Doug. Also, ahead, just Doug. Thought about that was also, it depends what you're thinking of doing with those oil seeds. If you're thinking of going into the edible oil market and creating a niche market that way rather than making biodiesel, that's a different set of numbers than if you're making fuel from it.
Excellent point.
Okay, thanks.
I'm going to just go
at the beginning quickly. So from Dan, he asks if there's any potential, you had mentioned the hazards associated with methanol, if there's any potential for using a catalyst other than methanol for biodiesel production.
Yeah, so one of the things being looked at is solid catalysts. So this is, think of the catalytic converter in your car that's doing a catalytic conversion process, and the same type of thing can be used for doing what we're doing here in biodiesel. Another liquid, and remember, the methanol is actually consumed. It's not a catalyst. The lye is the catalyst, but your point is the same. Ethanol can also be used, and ethanol can actually be produced sustainably. One of the research projects we've done is looked at a sugar-based ethanol production in the Northeast using sweet sorghum in support of this, in support of biodiesel production, and that pencils out quite well. The last area being looked at is more biological conversions. So, for example, there are some folks in Vermont here looking at in situ algae production of oil and follow-on conversion to biodiesel without any external catalyst.
Doug, would you mind taking this question on the feed for animal application, just to give Chris's audio a chance to sort of reset itself?
Okay. Chris isn't trying to answer the question how the solid material is used, and there are few uses for it. The major one is feed for animals. The meals have a fair amount of protein in them, generally not as much as soybean meal is kind of the gold standard at 46% protein. Canola meal is about the same. But that's the major use for it. Then the another use is fertilizer. It can be used as an organically certified fertilizer. Meals can be. And then a few people have mixed it with wood pellets to be used in pellet stove sort of application. That may not be the best way to use it, but you can use it in that form also, because it does still have some oil in it. The oil seed press leaves anywhere from 8 to 14% oil in the meal. And that is one of the big differences between these small scale presses and the commercial scale. Commercial operations use hexane to extract the oil, and they'll leave about 0.1% of oil in the meal, where we're leaving more like 8% or something along those lines in the meal.
Okay, we have, thank you. We have one additional question about economics. So Bryce asks about the costs for the setup that was shown for a small farm scale biodiesel production. I'm guessing this was he's referencing the example that you gave with the large, what were they, converted propane tanks standing up?
Yeah.
So you can tell me if that's the setup that you're specifically asking about.
In either case, it works out to about $1 per annual gallon of production capacity, and you can get more specifics on overall costs in that break-even economics report. But that's the general number, about $1 per annual gallon of capacity.
There's one last question. Do you have opinions on the highest and best use for oilseed crops? So I guess I'll direct this to both of you.
You can go first, Doug.
I guess my opinion is that the highest and best use for oilseed crops is if you take it and you use it for food first. You can take the used vegetable oil after you use it, either for frying food or however you might want to use it. Usually it's in fryers. Then it gets turned around and gets used to make biodiesel. You get food and fuel out of the same crop, which is a pretty neat combination. So I think that, to me, that's one of the better ways to go with it. I think also, I do believe that there's a place for making various edible oils out of it. That, whether it's the pumpkin seed oil or the canola oil or sunflower oil, you can make some really good tasting oils that should be able to be niche marketed and get reasonable returns for small farmers.
Chris,
This is
any thoughts?
Chris. I have a slightly different opinion. Yeah, can you hear me okay?
At the moment.
Are you able to hear me, Sarah? Okay, sorry.
Yes.
I have a slightly different opinion on that. I don't see the oil production for frying market for recovery to fuel as a real long-term solution when you consider that nearly 50% of the oil is lost in that process, and also I question the long-term nutritional sustainability of that model. So I think for culinary, high-end culinary salad oils, for example, yes, by all means, that's a very strong, there's a very strong case to be made for that. In terms of making fuel from oil seeds, I think we have a severe challenge getting to sustainable liquid fuels for agriculture in our nation, and I think oil seeds are one of the best pathways for that.
You mentioned some initiatives for algal and microbial oil production. How do you see that competing in future with traditional crops, land-based crops and oil seeds?
One of my concerns with algae has a strong yield potential on a per acre basis. My concerns are that the most optimal places for that production model are going to be areas with high incident solar radiation. Those also tend to be places with low water availability, and so those two things are necessary for that production model. And I worry that what's being demonstrated on the benchtop may not port to large-scale production. But if it can be done, then obviously there are very large potential yield gains.
Thanks. So I don't see any more questions in the chat pod. I know we ran a little bit late, but thanks for sticking around. At this point, I'd just like to thank both of our speakers. This is a lot of really great information. And thanks to our participants for joining us today.
Thanks, everybody.
Thank you.